Welcome to our practical guide on generalized linear models, focusing on estimation and inference using EViews. This presentation is designed for both researchers and students. As noted by Nelder and McClaw back in 1972, GLMs are a powerful extension of linear regression. They allow us to model relationships even when our data doesn't fit the classic assumptions, specifically when we have non-normal errors or nonlinear relationships. For instance, if you're trying to model the number of patents a firm produces, you're dealing with count data that can't be negative and isn't normally distributed. A standard regression would be inappropriate, but a GLM is perfect for this scenario. So, why exactly do we need to move beyond the standard methods we're all familiar with? Let's look at the limitations of ordinary least squares. The first major issue with ordinary least squares, or OLS, is its inability to handle bounded outcomes. As illustrated on the left, for binary variables like a lone default, which can only be 0 or 1, a linear OLS model can produce impossible predictions, like probabilities greater than 1 or less than 0. Secondly, OLS assumes constant variance, known as homoscedasticity. However, data types like counts or binary outcomes inherently exhibit non-constant variance, a condition called heteroscedasticity, which violates this core assumption. Finally, OLS fundamentally assumes normally distributed errors, which rarely holds true for discrete or bounded data. Generalized linear models, or GLMs, provide a robust framework that directly addresses these limitations. For instance, imagine modeling the number of children in a family. An OLS model might predict negative values, which is impossible, whereas a GLM like a Poisson model would inherently constrain predictions to non-negative counts, offering a much more realistic result. Given these limitations, the GLM framework offers a clear path to choosing the right model for our specific data. The journey starts with your dependent variable, y. Is it continuous and unbounded? If so, a standard OLS model, which uses a normal family and identity link, is appropriate. If your y is binary, representing a yes-no outcome like a lone default, you should use the binomial family. The typical link functions here are Logit or Probit, leading to logistic or Probit regression. For count data, such as the number of strikes or website visits, the Poisson or negative binomial family is the correct choice, almost always paired with a log link to ensure positive predictions. Finally, for positive, continuous data that is skewed, like wages or insurance claims, the gamma family with a log link is a powerful option. If you are analyzing the number of bids on an online auction, for example, this decision tree would guide you directly to the count branch, suggesting a Poisson or negative binomial model with a log link. This decision tree mentions family and link. Let's break down what these components mean in the anatomy of a GLM. Every generalized linear model, as shown in this equation, comprises three core components. First, the random component defines the probability distribution of the dependent variable, y, our family, such as normal, Poisson, or gamma. Second, the systematic component is the familiar linear predictor, a linear combination of our explanatory variables. Third, the link function, denoted by g, is crucial. It connects the expected value, or mean, of y to the linear predictor. For instance, in OLS, the link is identity, so the mean of y directly equals the linear predictor. But in a Poisson model for count data, the log link is typically used. This log transformation is vital because it ensures that predicted count values are always positive, even if the linear predictor is negative, enabling GLMs to model diverse data effectively. First, the observations must be independent. This is similar to the no serial correlation assumption in time series analysis. Each data point should not be predictable from the previous one. Second, the model must have the correct specification. This means you've chosen the appropriate link function and included the correct set of predictors in your linear model. Third, and this is a key difference from OLS, GLMs have a specific mean-variance relationship. The variance is not constant, it is a function of the mean. The formula is var of y equals phi v of mu, where phi is a dispersion parameter and v of mu is the variance function. A common violation of this is overdispersion, especially in Poisson models where the mean is assumed to equal the variance. If the variance is much larger than the mean, our standard errors will be incorrect, leading to flawed inference. For instance, in a Poisson model for traffic accidents, the theory assumes the mean number of accidents equals the variance. However, in reality, the variance is often much higher due to unobserved factors. This is overdispersion, and failing to account for it would make our results seem more statistically significant than they truly are. To fix this, you can use quasi-maximum likelihood, or QML, which are essentially Huber-White robust standard errors. Getting the model right is one thing, but how do we translate the results into meaningful economic insights? This depends heavily on the link function we chose. Now that we understand the structure and assumptions of generalized linear models, let's dive into how to interpret the coefficients correctly, as this heavily depends on the link function we've chosen. For the identity link, typically used in ordinary least squares, the interpretation is straightforward and additive. A one-unit change in your explanatory variable, x, leads directly to a beta unit change in y. However, when using a log link, common in Poisson or gamma models, the effect is multiplicative. For instance, if your beta coefficient is 0.05, a one-unit increase in x leads to approximately a 5% increase in y. This is a crucial distinction, often called a semi-elasticity. For the Logit link, used in binary models, the coefficient beta represents a change in the log odds of the outcome. While its sign indicates the direction of the effect on probability, for a precise magnitude, it's essential to calculate marginal effects at the mean of your variables. This brings us to a critical warning. Never say a one-unit increase in x leads to a beta increase in y, unless you are using the identity link. For all other nonlinear models, always consider marginal effects for precise interpretation. Now that we have the theory down, let's move to the practical side and see how to implement these models in EViews, starting with a case study. To begin estimating a generalized linear model in EViews, you have two primary methods for accessing the estimation dialog. The first is through the graphical user interface. You start by selecting the Quick menu from the main toolbar. From the dropdown, choose Estimate Equation. This action will open the equation estimation dialog box. Within this dialog, you'll then need to change the estimation method from the default to GLM, Generalized Linear Models, which you can find in the dropdown list. This sequence of steps will bring you to the point where you can specify your GLM. For those who prefer a more efficient workflow, EViews also offers a power user shortcut. By simply typing equation eq1.glm into the EViews command window, you can bypass all the menu navigation. This command immediately opens the GLM specification dialog, allowing you to quickly enter your equation and chase your desired family and link functions, such as Poisson with a log link, as we discussed earlier. This slide shows the critical Specification tab within EViews' GLM estimation dialog. This is where we define our model. First, you'll enter your equation, starting with a dependent variable, followed by the intercept c, and then your chosen regressors. For our strike example, this would be num_c ip feb. Next, you'll select the appropriate family from the drop-down menu, which for count data, like our number of strikes, is Poisson. Below that, you'll select the link function. For the Poisson family, EViews intelligently auto-selects the log link as its canonical default, ensuring predictions are always positive. However, it's crucial to remember that you can override these defaults if your specific modeling needs require a different link function, for example, using a Probit link with a binomial family. Once you've specified your generalized linear model in EViews, you'll want to navigate to the Options tab to fine-tune your estimation. Here, several crucial settings ensure the robustness and validity of your results. First and foremost, under Covariance method, it's essential to select Huber-White. This option provides quasi-maximum likelihood, or QML, robust standard errors. As highlighted by the robustness tip, you should always consider checking Huber-White if you suspect overdispersion, a common issue in GLMs, especially with Poisson models where the mean variance assumption might be violated. Using Huber-White makes your statistical inference valid even if the variance assumption fails, giving you greater confidence in your p-values and significance. Other important settings on this tab include max iterations for convergence, which can be adjusted if your model struggles to find a stable solution, and initialization, allowing you to set starting values for the estimation process. To make this practical, we'll replicate a classic study by Kennan from 1983 on industrial strikes. Our goal is to model the number of strikes. The dependent variable is num, which is the count of strikes. This is a discrete, non-negative integer, making it a perfect candidate for a count data model. Our regressors are IP, which stands for industrial production, and Feb, a dummy variable for the month of February. Looking at the histogram, the data for num is clearly not normal. It's skewed to the right with a long tail, which strongly suggests a distribution from the Poisson family. Since our dependent variable, the number of strikes, is a count, the GLM decision tree points us directly to the Poisson family with a log link. This ensures our model will predict a non-negative number of strikes. To execute our GLM and EViews, we have two primary approaches. The graphical user interface, or GUI, method involves filling out the estimation dialog box, as we previously discussed, selecting the Poisson family and log link for our num-CIP Feb equation, and then clicking OK. This is a very intuitive approach, especially for those new to EViews. However, for more experienced users, or when performing repetitive analyses, the command line offers significant efficiency. The syntax is concise. You start with equation, followed by a name for your equation, such as EQ strike, and then .glm to specify a generalized linear model. Within parentheses, you define the family and link using F equals for family, which is Poisson in our case, and L equals for link, which is log. Finally, you list her dependent and independent variables, num, CIP, Feb. This single command executes the entire model specification and estimation, mirroring all the selections made in the GUI. When you generate your GLM output in EViews, the very first and most crucial step is a sanity check. Look at the top line for the convergence status. If EViews reports convergence not achieved, your results are invalid. This means the estimation algorithm failed to find a stable solution, and you would need to adjust parameters like increasing the maximum number of iterations or providing better starting values. Fortunately, in this example, we see convergence achieved after 4 iterations, confirming our results are reliable. Next, we examine the table of coefficients. The coefficient column provides the estimated beta values for each variable. For instance, IP, industrial production, has a coefficient of 0.025. To assess the statistical significance of these coefficients, we turn to the prob column, which displays the p-values. A p-value less than 0.05, such as the 0.0000 for IP, indicates that the coefficient is statistically significant at the 5% level. This gives us confidence that industrial production truly has a measurable effect on the number of strikes. Now that we have these statistically significant numbers, let's explore what they mean in economic terms. Let's now delve into the economic interpretation of our results for the industrial production variable. We found that the coefficient for industrial production, or IP, is 0.025. Given that we used a log link function in our Poisson model, this relationship is interpreted as semi-elastic and has a multiplicative effect. This means that a 1-unit increase in industrial production is associated with an approximate 2.5% increase in the expected number of industrial strikes. This is an important economic insight. It suggests that strikes are pro-cyclical. In other words, during periods of a booming economy characterized by high industrial production, labor tends to have greater bargaining power, which can lead to more labor disputes and, consequently, more strikes. Furthermore, the statistical significance of this relationship is very strong. With a probability or p-value less than 0.05, we confidently reject the null hypothesis that industrial production has no effect on the number of strikes. This confirms that our findings are not due to random chance. With this interpretation in hand, we need to ensure our model is robust and reliable, which leads us to perform crucial diagnostic checks, particularly for overdispersion. A critical diagnostic check, especially for count data models like Poisson, is to ensure our assumption that the mean equals the variance holds true. To perform this variance check, we look at the deviance statistic divided by its degrees of freedom in the EViews output. If this ratio, deviance over degrees of freedom, is significantly greater than 1, it indicates that our data suffers from overdispersion, meaning the variance is much larger than the mean. The consequence of ignoring overdispersion is severe. Your standard errors will be too small, making your results appear more statistically significant than they genuinely are, leading to potentially flawed inferences. Fortunately, there are two effective fixes. First, you can switch the model family from Poisson to negative binomial, which is designed to explicitly handle situations where the variance exceeds the mean. Alternatively, you can keep the Poisson model, but elect to use Huber-White robust standard errors, also known as quasi-maximum likelihood (QML) standard errors, available in the Options tab. These robust standard errors will correct for the misspecification caused by overdispersion. To summarize our discussion, here's a concise workflow or cheat sheet for implementing generalized linear models in EViews. First, always begin by clearly identifying the nature of your data. Is your dependent variable binary, a count, or perhaps positive and skewed? This initial assessment is paramount. Second, based on your data type, select the appropriate family and link function. For instance, binary choice data typically uses a binomial family with a logit link, while count data often requires a Poisson family with a log link, and skewed wage data might use gamma with a log link. Third, proceed to estimate your model in EViews, either through the intuitive menu system or via the efficient command line. Fourth, it's crucial to check your results for validity. Confirm that convergence was achieved, and diagnose for issues like overdispersion by examining the deviance to degrees of freedom ratio. Finally, interpret your findings correctly by applying the inverse link function logic to understand the effects of your variables. Remember, GLM truly unifies statistics by providing this flexible framework. The most challenging aspect is correctly choosing the underlying data distribution. EViews simply makes the estimation seamless once that theoretical understanding is in place. We've reached the end of our discussion on generalized linear models. I'd like to extend my sincere thanks for your attention and engagement throughout this presentation. As we reflect on the complexities of model selection and interpretation, the timeless wisdom of George Box reminds us that all models are wrong, but some are useful. Our goal with GLMs is always to strive for those more useful models.